Now dealing with intracardiac pressures, we discussed extensively what the Bernoulli equation is and how it has been modified and simplified for clinical use. And when we bring it to bear, it gives us a lot of advantages in the calculation of intracardiac pressures, which is what it's designed to do in the first place. Pressure gradient across any valve is 4 multiplied by the square of the peak velocity. Like we all know it has been simplified Bernoulli equation. And this allows for pressure calculation from an already known or estimated single chamber pressure, such as the right atrial pressure. We mentioned it earlier that the value of RAP will be very useful if we, after estimating or after the estimation of the right atrial pressure, we already know what the pressure is in a particular chamber. We can calculate either forward or backward using the Bernoulli equation to arrive at other chambers, backward or forward by the knowledge of a particular chamber, such as the RAP. This is possible because when the lumen of a fluid system narrows, the fluid accelerates, thereby increasing kinetic energy, which is the peak velocity. This increase in kinetic energy must be offset by a decrease in pressure energy for the total energy of that system to remain constant. Conservation or energy conservation principle, which is what Bernoulli is about. Conversion of velocity, which you can calculate, to pressure, which you might not be able to calculate directly through the principle of energy conservation. So when there is a narrowing, such as valvular stenosis or obstruction on a particular path, it gives us the opportunity to use the increase and offsetting of the kinetic energy at that point to convert it into pressure, which gives us an idea or allows us to use that particular pressure conversion from a known chamber pressure to calculate the one that is unknown. Don't bother your head with the complexity. I will show you examples of how these are done. For example, a non-systolic blood pressure of 130 millimeter mercury measured using the SFIG can be used to generate left ventricular systolic pressure and calculate left atrial systolic pressure. Because there is a way we can generate the systolic blood pressure using the SFIG, that particularly known pressure from that method can be used, interpolated, to generate the left ventricular systolic pressure and to calculate the left atrial systolic pressure. How? The left ventricular systolic pressure will be the same as the already known systolic blood pressure of 130 millimeter mercury because of the principle of total energy conservation in fluid dynamics, which we just explained earlier. Provided there is no obstruction, such as the LVOTO, left ventricular flow tract obstruction. Why is this? It's because the pressure that is calculated using this SFIG in the brachial artery is the same as the pressure being generated from the left ventricle driving the blood originally. The pressure that is generated by the left ventricle or left ventricular myocardial wall to drive the blood out of the left ventricle into the aorta, it will be the same as the one that is calculated, generated by the SFIG at the brachial artery, because of the principle of total energy conservation in fluid dynamics. It will remain the same, provided that there is no obstruction, particularly at the LVOT, that will have distorted the pressure flow. If there is no obstruction, then be sure that whatever you are calculating with your sphic will be the same as the pressure in the left ventricle during systole. In the presence of a mitral regurgitation, left atrial systolic pressure, now the left atrium, now not the left ventricle, can be calculated using the simplified Bernoulli equation on pressure gradient across a narrowed orifice, such as the mitral valve. When there is regurgitation, you know the valve is like a narrowing between the left atrium and the left ventricle. Those are two chambers, which ordinarily their pressure should have been the same following fluid dynamics. However, because there's a narrowing, which is the valvular passage, in this case, the mitral valve, there will be difference between them. So if we can get the pressure gradient across the narrowing, it can give us an idea of what the pressure is in the other chamber, knowing the one from the other hand. Remember, we already know the pressure in the left ventricle during systole. Now there is a narrowing, which is the mitral valve. If there is an MR, mitral regurgitation, we can use that advantage to calculate what the pressure is in the left atrium. Because from that regurgitation, we can calculate what the pressure gradient is. And when we know what the pressure gradient is across that mitral valve, it's just a simple mathematics of subtracting that pressure gradient from the already known left ventricular systolic pressure. It gives us what the left atrial systolic pressure is. It's as simple as that. Just by subtracting what the pressure gradient is across that mitral valve from the already known left ventricular systolic pressure, which we extrapolated from the sphic. You remember how we got there? Extrapolation from the sphic, provided there is no left ventricular flow tract obstruction, will be the same as our left ventricular systolic pressure. We already know that. If there is now an MR will allow us to calculate the pressure gradient between left atrium and left ventricle. Once we know what is between them, it's only a matter of subtracting that from the left ventricular systolic pressure to know what the left atrial systolic pressure is. Oh, we have it here. When the MR Vmax, because that is what you can measure, you can't possibly measure the pressure. What you can measure is the mitral regurgitation maximum velocity. When you do that, you measure the maximum velocity at the peak here, which in this case is 5.4 meters per second. Using the formula, the Bernoulli now, pressure gradient across the mitral valve between the left atrium and the left ventricle can be gotten using the Bernoulli, the simplified Bernoulli, which is 4 multiplied by square of the maximum velocity. And that gives us what? 118.37 millimeter mercury. This is the pressure gradient between the left atrium and the left ventricle. And you remember that this patient has 130 millimeter mercury as the left ventricular systolic pressure measured or as measured by the sphic. So it's just a matter of subtracting the pressure gradient between the two chambers, between the left atrium and the left ventricle, and it gives you what? Your left atrial systolic pressure using this example. So, and ultimately become more.